Okay, so let's move on. So we've talked about projectiles or suvat in two dimensions. I know we've done a couple of examples that weren't specifically projectiles. And we've talked about doing it with or without vectors. But in every situation, the acceleration was constant. And it's really important to identify when you get a question that are we dealing with constant acceleration or are we dealing with variable acceleration? And you may remember this from last year that if acceleration isn't constant, we can't use the suvat equations, but there is a relationship between the three quantities that we're interested in: displacement, velocity, and acceleration. Moving up the ladder, we're differentiating. Moving down the ladder, we are integrating, although I note that CGP, they put their ladder the other way up, but anyway, it's all the same stuff still. So before we move to the second year stuff, I thought it'd probably be good just to remind ourselves about this in the stuff we did last year. So I quickly turned to Maths Genie and looked at the AS mechanics and statistics stuff and found this question here. Question 4 we're going to look at. So we're given here a formula for velocity. It's a formula that changes after 5 seconds. So this is the velocity after for the first 5 seconds, and this is the velocity after that. And we're asked to find acceleration when t is 4, and we're asked to find the total distance travelled in the first 10 seconds. So when t is 4, I'm dealing with this first formula here. So acceleration is what you get when you differentiate the velocity, dv by dt. So this is my formula for v when t is 4, and so I'm just going to differentiate that, so that's going to give me 7 minus 2t. When t is 4, that becomes, I really should use little a, that's what we tend to use. So that's 7 minus 8, so that's a deceleration of 1 meters per second squared, or an acceleration of minus 1 meters per second squared. And so for part B, distance travelled, well, I know that to work out distance I need to integrate velocity. So I've differentiated velocity to get acceleration, I need to integrate it, and I need to integrate these two separately. So the first one I need to integrate between 0 and 5, and then I also need to integrate the second one between 5 and 10, and both of those are with respect to t. So it's two quite straightforward integrations. So go on, pause the video, see if you can do them separately, and then interpret what you get to tell me the total distance travelled in the first 10 seconds. Okay, so on this side, integrate it, substitute in 5, substitute in 0, that gives us that many meters. And on this side, we get 2t squared over 2, which I just simplify straight away to t squared. And we get minus 25, but of course we're talking about the displacement. So minus 25 just means something about the direction, but it just means a distance of 25. So my answer is that plus 25, which gives me 425 over 6 meters. So if we move to the our mechanics book, I'm on page 90, and it's evening here, and the light isn't very good, I have to say, so I apologise if it's a bit sort of a bit swimmy. But yeah, so they use the same diagram as me, but they've done it in reverse. But when we move into 2 dimensions, it's sensible to use the word position rather than displacement, because displacement, you're talking about how far from a start point moving in one direction, whereas now we're talking about 2 directions. So the use of the word position is good, and note that they're using letter R to stand for position. But you still differentiate to get velocity, and then again to get acceleration, and you integrate back again. However, the thing some of you will have thought, well, hang on a minute, but what about when we are describing these things using a vector? And, well, I mean, I could write it. I think the book, one of the reasons I like these books so much is they explain things so clearly. So if you've got a formula for position and it's in vector form, then it is as easy as anything to find velocity. You just differentiate that expression, which basically means separately differentiating the I part and the j part, just separately. And then to work out acceleration, you just differentiate again. You differentiate the parts separately, and surprise, surprise, to go the other way, if you start with a formula for acceleration, for example, then to work out velocity, you integrate this, and that just means integrating the two components as separate expressions, and then integrating again to get a formula for position. So all good, nice and easy. Let's do an example. As before, the book has a number of worked examples that I don't intend to go through, but I think they're good if if I don't do a very good job. I do like the way this book explains things. So we're going to jump straight to the exercise that comes after the worked examples. So here we are on page 95, and there's the first question that we're going to do. Again, I'll leave it there so you can screenshot it if you haven't got your copy of the textbook. But yeah, let's work through this. So we've got position described as a vector, and you know what I'm going to do straight away? I don't want to disappoint you. I'm straight away going to write that in column vector form. So, here's the formula in column vector form. And the first part of the question says find an expression for velocity. So remember the diagram, you go from, there we go. So we've got a formula for position. So to go to velocity, I'm going to differentiate. I know that's the other way up to the way I've done it, but it's still differentiating. So I'm going to differentiate this, and I'm going to differentiate that. And so I can write that in IJ notation as well. So that was, sorry, I'll turn the page again. So that was part A1. So now we want the speed and direction of motion at the time when t is 3. Okay, so let's make t equal 3. So that means that the velocity becomes 3 lots of 3 squared, that's 27 take away 3, so that's 24, and 2 lots of 3 is 6. So that's the velocity in vector form, which means that we're 24 meters per second in this direction and 6 meters per second in this direction. So that's the actual direction of motion, and so I'm going to use a little bit of Pythagoras and a little bit of shift tan to work out the size of the speed, the magnitude of the speed, and the angle at which it's going. I'll pause and get you to do that as well. Okay, so I think before I paused I was a bit bad with my use of velocity and speed. So this is the velocity, which is the described in terms of the separate horizontal and vertical components. And here we've got the speed, which is 24.7 meters per second at an angle of 14.0 degrees to the horizontal. We're then asked to find an expression for the particle's acceleration in part B. So I'm just going to differentiate my velocity expression. So it's going to be 6t and 2, or and the magnitude of the particle's acceleration when time t is 4. So So 6 times 4. So that is the acceleration, and its magnitude will be the square root of 24 squared plus 2 squared, which is 24.1 meters per second squared when rounded to 3 significant figures. Easy peasy. Okay, that's better. It's daytime now. So we have a go at question 4 next, page 95, question 4. This is unusual in that they give the vectors as columns, but we are this time given a formula for acceleration, and we're asked to find an expression for velocity and position. So this is going to involve integrating, and it introduces an issue which some of you might have already had in your mind, but we'll approach it now. So let's go with the formula then. So the formula is 3e to the 3t and 6 over the square root of t, which I'm going to write like that. So I'm going to integrate those two things separately, and so when I integrate e to the 3t, I get e to the 3t divided by what you get when you differentiate the power, which is 3, but it's already multiplied by 3 at the front, so they cancel each other out, so I'm just left with that. And here, increase the power by 1, divide by the new power, which is dividing by a half, and which is the same as multiplying by 2, and we've already got a 6 out the front. But of course, when we integrate, both of these have got a constant, and there's a bit of an issue here, isn't there? Because I've got, this isn't going to be the same necessarily, so I'm going to call both constants something different. I note that the book does this slightly differently. It sort of writes the constant as a separate column vector, which it then folds in, but I'm going to persist here. Now, we often have this when we are using integration to undo differentiation to get the formula for a function, and they normally then give us a point which we can substitute in to work out the value of c, and that's what we've got in this one, haven't we? We've got a position vector and a speed when t equals 0. So I'm going to substitute in, so what I've got now is a velocity equation. So I'm going to substitute in t is 0 into this. And I know that at t is 0, the velocity will be 4/6, so this will be 4/6. So go on, substitute in t is 0 into this and see if you can tell me what the value of the two constants are. Okay, so c is 3, k is 6, so what I can do is sort of feed that back into here. So my formula for velocity, my expression for velocity is, and otherwise the question was used I and k notation. I want to do the same. Now, I note that in the book it wrote this as that plus a separate vector, and it said so the separate vector was 3i plus 6j, but then they rolled it back in together to get the same final answer as me. So the book uses a slightly different approach, but there we go. Okay, so we've got an expression for velocity. So we now are asked to find an expression for position, and we know that that just requires us to integrate velocity again. So this is our expression for velocity. We're going to have the same issue with constants, but we've got another fact given to us in the question this time about the position. So go on, have a go at finishing off that question, starting with this and integrating it to get a formula for position, which remember we use R for. R equals the position. Okay, so I took the formula for velocity and integrated it. So e to the 3t, power stays the same, divide by what you get when you differentiate the power, so, which I chose to write as a third of. You could have written it over 3, same thing. 3, when you integrate, becomes 3t, and then we've got a constant. And then here we increase the power by 1 and divide by the new power. 12 divided by 3 over 2 gives you 8. 6 becomes 60, and you've got another constant. We're told that when t is 0, the acceleration, the position is 2 minus 9. I used the velocity one to start with incorrectly. So I substitute 0 into this, and I just get 1/3 of 1. Anything to the power of 0 is 1 plus c, and this just becomes k. And that gives me my values of the constants, which I can feed back into that. And I've left it in column vector form, but of course I could write it in I and j notation. So that's the basics. So I guess the sort of the final step is just to do a bit of slightly more complicated problem-solving style questions. Actually, it's interesting looking at the pre-release information. With variable acceleration, there's no mention of vectors, which makes me, whereas it does mention vectors elsewhere, which makes me wonder if it might just be a year 1 question that comes up. But anyway, I think for completeness we need to cover this. So so here's a question where we're given a formula for position, displacement, and we're asked in the first case to show the distance from the origin is constant and use this information to fully describe the path of the particle. Now, what we're effectively saying here is that the position of this is always this in the x direction and this in the y direction. So what this is effectively is parametrics. And you may remember what happens when you have a parametric function described where y is something to do with cos, and x is something to do with cos, and y is something to do with sine, or vice versa. Sorry, we're on page 96 now, question 7. So let's draw a little sketch of the position of this thing from the origin, and what we're told is that that's always 8 cos t, and that's always 8 sine t, and we're told to show that its distance from the centre is always constant. So let's square and square root. So that squared is, you see where we're going here? And that squared is, add those together. So that's going to be sine squared plus cos squared is 1. So that's 64, which of course is that length squared. So the distance is always going to be the square root of 64, which is 8. I apologise, that's a dreadful diagram. I'm embarrassed. But this is going to be on the public internet, but there we go. So it's the square root of that. So whatever the value of t, the distance from the origin of this particle will be 8. And so if something is moving in a path where it is always the same distance from where it starts, from the origin, then that's a circle, isn't it? So actually, we could show separately using parametrics that if you have x is 8 cos t and y is 8 sine t, you end up with the equation of a circle. I tell you what, should we do that? So if instead this was described using parametrics, and you remember when you're trying to turn a parametric into a Cartesian and it involves trig, you need to pick an identity. Well, both of these I can rewrite as sine equals and cos equals, so I can rewrite this one as and I know that sine squared t plus cos squared t always equals 0. That's my identity that I've picked because I've got an expression, I've got coses and sines. So sine squared t will be y squared over 64, and cos squared t is x squared over 64. I hate the fractions, and I'm going to switch my x's and y's around. So hopefully you recognise that that is the equation of a circle with centre 0, 0 and radius 8. So that, you know, this is the same sort of thing. Vector, parametric, it's the same thing. Anyway, so the answer to part A is that the path of the particle is a circle with radius 8. Okay, so we've got to find an expression for acceleration. So we've got an expression for position, displacement, so that's going to require differentiating twice. So I'm going to pause and get you to have a go at that. Okay, and the more eagle-eyed amongst you will spot that this is just minus this, and then if I went through this process again with the acceleration equation, you'd get the same outcome, wouldn't you? You'd get we're dealing with something else that's moving in a circle, although of course acceleration is not the position, but the way the acceleration is varying. So we're asked this rather odd question, aren't we, about determine whether each of the following statements is true or false. A varies with time, and then the magnitude of A varies with time. Well, I'm going to answer the bottom one first. This is the same as we answered up here. This was the magnitude of the distance from the origin, the position. This was the magnitude, and it was constant, it was 8, and so we're going to get the same here. So for part 2, no, it doesn't vary with time, it's going to be 8. It's going to be 8. So the acceleration, the magnitude of the acceleration will always be 8. However, the acceleration itself, well, both of these are going to vary as t varies, aren't they? We know that cos t will vary between -1 and 1, and sine t will vary between -1 and 1 as you change the value of t. So it's slightly odd to get your head round. The acceleration is going to change, but the magnitude of the acceleration is not going to change. So this particle will be accelerating in different directions in different ways. This is describing the x acceleration, and that's going to vary between -8 and +8. And this is describing the y acceleration, which is going to vary between -8 and +8. But the overall magnitude of the acceleration will not change. That will stick at 8. So part 1, A does vary with time because the x and y components will both vary, whereas the magnitude does not vary with time, so the statement here is false because the magnitude of this will always be 8. Okay, so that's the last in terms of the examples I'm going to go through. I think in terms of ones for you to try, it's worth having a look at question 3, where you're given a velocity and you're asked to find a maximum velocity. This is a turning point question. How do we find turning points? Well, we differentiate our function and ask when does it equal 0, and they're sort of giving us that hint there. The car reaches its maximum velocity when the acceleration falls to 0. So you're going to differentiate this to get a formula for acceleration and then ask when does it become 0. So page 95 and question 3 I would say are definitely worth doing. And then I think question 8, another one where you are given a formula for velocity, asked to find acceleration, and question 9, which is one where you're given acceleration and you have to work backwards. So there's a little bit of both integration and differentiation there. But goodness me, you're smart people, you can decide what you want to do from those questions. So I am recommending page 95, question 3, and page 96, question 8 and 9. The basic mechanics of what we've done, mechanics, see what I did there, it's very straightforward, isn't it? We're either differentiating or integrating vectors, which we can do by differentiating or integrating the separate x and y components, the I and j components. And the only slightly confusing thing is when you are integrating, it introduces that constant issue, which you have to look in the question to find some values that they've given you to help you work out the value of the constants. Okay, so that is the end of that particular issue, variable acceleration, and that really finishes the new content. So what I'm going to do is 3 more videos over the course of the next week, looking back at and extending things we've already done. So I'm going to look at ladders again, and some slightly more complicated examples involving ladders. Have I mentioned that I think ladders might come up? I'm going to look at connected particles again, because that's quite complicated. And also, actually, I'll say that's the end of the new content. Related to ladders and moments, we didn't do any questions involving hinges, and hinges are worth doing as well. So I'll do a video on hinges. I know a couple of you have asked about laminas. I see no evidence at all that they're going to be laminar questions in the exam. I may well knock out a laminar video as well if time allows. But there we go. Crack on with those. Please keep in touch, and hopefully you are managing to be productive with your revision and having a good break at the same time. Take care.